So we're going to give you a whirlwind overview of all of the different storage products that we have on Google Cloud Platform, and give you some pointers as to where to think about storing all the different types of data that you might have. So I'll kick us off, and then I'll invite some of my colleagues onto stage as we progress through the presentation. So agenda. So first of all, actually, I want to just kind of do a little sort of journey through time and talk a little bit about some context as to where we are in the sort of the journey of the different types of storage that have existed over the last 40 or 50 years, and sort of set that context for where we are today. Then we'll go through some of our storage products in more detail, and then our database products as well. All right, so first of all, just a brief history of storage and databases. So let's start off with storage, first of all. So go back far enough, or just look under your desk, and you'll find that the original way that storage was attached to compute was it was just physically attached to the CPU, right? So for all the desktop machines that you have, for the computers that came out long, decades and decades ago, you just bought a physical box, you ran your application, the file system, and the storage, all attached together as a single thing. So storage was what was called direct attached storage. It was just physically attached to the machine. That obviously became quite inefficient as the amount of data grew, the amount of CPU resources grew, and the idea of storage over a network evolved into two main categories: storage area networks and network-attached storage. In the first storage area networks, here the main idea is that the network is separating the storage from a set of machines that are storing effectively blocks of storage, and the file system is local to the machine which is running the application. And the reason this was important is what this allowed you to do is operate locally on files in your compute instance, but over the network, communicate in large blocks of storage. So you'd communicate with an 8K block, or a 16K block, or a 64K block. So you'd hand back and forward big blocks of storage to the underlying storage infrastructure, and then operate your application over the file system. So that was pretty good for particularly database-type applications that wanted to be able to do lots of sort of management of the storage locally, and then sort of hand off big blocks of storage back to the storage system. So this was the era of SAN, storage area networks, probably one of the best-known products in this area. The other category, network-attached storage. So this is now your typical kind of file storage or file share, which is over the network. So your application sits on a set of machines, you have a network, and the file system is sitting remote. So that remote file system is dealing with things like locking of files and remote access to the various storage systems that you have. And then more recently, object storage started to come to fruition. And this was for a class of storage that was typically really, really large and structured blobs, binary large objects of data, where you wanted to store a really large amount of data and just have very simple get and put kind of operations on it, for which the semantics of file systems were too rich, and often the costs were too rich. So a class of object storage started to materialize. Actually, that really only took off in the cloud era, but there's plenty of on-premise storage options available. So that's kind of the history of the storage systems that are out there. And then Google Cloud Platform offers a set of equivalent products for that from storage. So that's persistent disk and local SSD for direct attached block storage, file storage with Cloud Filestore, and then Google Cloud Storage for object storage. In the world of databases, actually a bit more complicated a journey. Actually, it was pretty simple. For 30 or 40 years, there was 2 or 3 major database vendors who built proprietary OLTP systems on which you gathered your transactional records. And when you wanted to run queries and reports on them, you really didn't want to run a large-scale query against your transactional system. So you decided to take all your data off in batches and run it through a process called ETL, extract, transform, load, store it into a specific system called a data warehouse, where you'd now model the data for the types of questions that you knew you wanted to answer, using Snowflake schema and other things like that. And for 30 or 40 years, this was the norm, right? So transactional records captured on a transactional scale-up database system, data was ETL'd off onto a data warehouse where you do analytics and reports. And for 30 and 40 years, that was the state of the art. These systems sort of scaled up. They got bigger. They got more powerful. And then around the time the internet emerged, the world became much more connected. The amount of data that could be collected really ballooned in volume. And also in the variety, right? No longer were transactional records the only source of interesting data that organizations might want. They wanted to capture log data, stream data, click data, analytics data. And it's just really, really inefficient and not cost-effective to store that into a transactional database. So it all started getting dropped into basically unstructured log storage. And folks would just drop lots of storage onto cheap storage systems, and then had this huge challenge of like, well, how do I now mine that data, right? And so this is where the sort of Hadoop ecosystem started about 15, 20 years ago, came to fruition, where you wanted to be able to capture huge amounts of unstructured data and then run jobs over that data to sort of refine it in place and find the interesting insights that you would then often put into a data warehouse to serve and run analytics on. So that started to happen on the analytics side. And then on the database side, two other very interesting things happened. There was a lot of so the need to sort of store very wide column tables. So this is like thousands of different potential columns on a table, and store that at extreme scale. And that, again, just became something that was quite inefficient to do with a traditional relational database management system at the time. So a whole class of wide column databases emerged to support that use cases, where you're looking for sort of key value lookups really fast. Another one that emerged was in the sort of this NoSQL category is a document database. So you might be working with, say, a JSON document. So it has a sort of semi-hierarchical structure. It's not something that works super well with a transactional system, where you're more traditionally storing, customer and orders, and having a nice, strong relationship between them with foreign keys and other relational constructs. You wanted a much looser way to manage hierarchical data, and so a whole class of document databases emerged to support that. And these sort of so-called NoSQL databases made a number of trade-offs in terms of how they thought about the semantics that you got over the data. Traditional relational database management systems gave you really, really strong relational semantics. You could have tables, relations between them, foreign keys, transactional consistency, the ACID properties of transactions. There was a very strong mathematical model behind those to give a set of very powerful constructs. But they're all very constrained within this effectively scale-up architecture. The NoSQL databases effectively said, look, we're willing to give up on a couple of things in order to get the scale and the performance that we need, right? In particular, these were originally sort of eventually consistent models that much more easily let you scale and get availability, but at the cost of consistency of your data. And now more recently, there's a new class of scalable relational database management systems that have come to the fore that have really fundamentally tackled some of those, addressed some of those fundamental issues of this balance between scale and availability, and now have actually brought some really interesting technology to bear, where I think if we look forward, in 10, 20 years' time, we'll actually see a number of these solutions kind of coalescing back together again, certainly in terms of the semantics that they provide on the back end, while still providing really easy interfaces to deal with things like documents, etc. So that's a sort of a brief overview of the history of storage and databases. Oh, actually, sorry, let me go back. For Google Cloud Platform, we, of course, have a great set of offerings for each of those different classes of databases, from Cloud SQL for both MySQL and Postgres, BigQuery for data warehousing, Cloud Dataproc and Cloud Storage is great for the large-scale Hadoop data lake use case. For NoSQL, we have Bigtable and Firestore, and then Cloud Spanner is our scalable relational database management system as well. And we'll go into those in more detail later on in the talk. Okay, so that's a sort of a summary of the history and sort of where we are in the in the industry right now. There's a summary of all the different products that Google Cloud offers here, from in-memory through relational, NoSQL, data warehousing, and then object, block, and file storage systems. So let me now go through some of the storage products in a little bit more detail. Let me start with Google Cloud Storage. So this is our object storage product. So if you have really large amounts of data to store, media content, want to run a large-scale data lake, then Google Cloud Storage is the product for you. Fully managed object storage service, has a set of different tiers, letting you tier your data from the standard through nearline and cold line, giving you progressively cheaper cost in terms of the cost per gig to store it. We give you a single API to access all of that data. By default, all of the data is encrypted. Anytime you write data to it, anyone who's reading can immediately see that data, so we have strong consistency of the metadata. That's a really big deal if you're building a data lake on the platform. Super powerful product. Main use cases we see it used for content storage and delivery. So for example, Spotify storing huge amounts of media content and streaming that around the world. Data lake and analytics, so Twitter storing very many hundreds of petabytes of data to run large-scale Hadoop jobs, analytics jobs in the cloud on that. And then just data protection. So if I've got backup archival data, it's a great low-cost option for basically archiving your data to the cloud. Persistent disk. So this is our block storage product. So classic use cases here are if you're spinning up VMs and you want to attach a disk to them, then persistent disk is the product that you would use for that. More advanced use cases, if you're building highly available databases, then you want to have a disk product that you can attach for that. So big main use cases, general enterprise applications, also used for some big compute applications that want to run in regular VMs. We have 2 tiers of persistent disk, standard and high performance, which is backed by SSD. Couple of really nice features about this product is it's completely separate from the compute instances that you provision. So you can provision any compute instance, provision a disk. If you decide to increase the size of your disk, you can do that dynamically. If you decide to change your compute instance, you can do that dynamically. These things aren't coupled together, so lots of flexibility in building out and sizing your VMs, and also sizing out your disks. Another great feature, any one disk can scale to 64 terabytes. So if you've ever need to think about striping disks for better performance, you don't need to. We take care of all of that magically under the covers. So provision one 64 terabyte disk. Actually, under the covers, we write that out over hundreds and thousands of different disks. And so we get really good, consistent performance for you for your application. A couple of cool features we've announced recently is snapshots. So you can take snapshots of those disks, store them regionally, schedule them. And a feature that's just coming through beta right now, regional persistent disk. If you're building highly available database applications, super, super useful feature to give you an active disk that's synchronously replicated between 2 zones. So I might have a VM in one zone, a VM in another zone, and I can now have a shared disk that is synchronously replicated between those 2 zones. So super key feature for persistent disk. Cloud Filestore. So here you might just want regular sort of file storage, file share over the network, and we give you that with Cloud Filestore. So classic product used for many existing applications that are just expecting a file storage product to be available in the cloud. So we see that used for a lot of lift and shift applications, content manage applications, and again, batch compute applications that have been running against, say, the POSIX API. So again, comes in 2 tiers, standard and high performance, has great low latency and high IOPS, and again, nice flexible scaling way to scale capacity. Okay. Bringing data to the cloud, so transfer appliance. So if you have a large amount of data that you need to move to the cloud, and we see customers who are shutting down data centers, they're moving media content archives. Schmidt Ocean Institute is gathering oceanographic data on ships that are in the ocean, and they need a way to capture that data, right? So we provide the transfer appliance, which is a rackable form factor that we ship to you. You rack it into your data center, bring power, network, plug it in, and we can then load it up with up to a petabyte of compressed data, and then you ship it back to us. So we see, as I mentioned, a lot of customers doing this for just really large-scale migrations of data to the cloud. All right, so with that whistle-stop tour of the storage products, let me ask Gabby to come up on stage and just give you a quick demonstration of one of our storage products.
Thank you, Dave. OK. I'll be creating first. Dave mentioned that we have standard nearline and cold line storage for Google Cloud Storage. And here you can see I already have a bucket and it's cold line. That means retrieval usually it's not as fast as it would be at the standard. And to create a bucket with any of those storage classes, you just give it a name and choose which class you want in here. And the location is important. You want it to keep it closest to your application as possible, but that may not be a requirement for you because a feature that I'm going to show next. So I'm going to create this one that's multi-regional, and I'm going to show you one picture that's going to make everybody awe, which it is my puppy. So Ada is going to be being a part of this demo. I'm going to upload her picture to our code line storage system. That's in here. I already have a picture here, and it's public, and I'm going to upload a copy of it, the same picture. Oops. And uploaded, and it's there. The cool thing about Google Cloud Storage, even though it's a code line, and you can see here, I put it as in Asia right now. It's in Asia, this bucket. You can actually have real low latency because once you're inside Google's network, everything it's mostly one hop to get the data that you need on your application. So once you ping or API or storage API, you're going to see it took only one hop from the UK server to the storage API center. Because we have over 100 points of presence in the world, this is always going to hop to the nearest location to you. So how that translates to that image that I just uploaded on the code line. So if we try to get that image, and wait a moment. And I put it as Ada copy. It took almost 1 second to retrieve it. And if you try it again, it's also almost 1 second. Because it's not being cached, and this image is not available for you publicly. However, if you try with the public image that I just showed you, you're going to see here code line and 0.019 seconds to get the image, and that's on code line. And so once you make the image from private to public, you take advantages of Google network, whereas that image is also available here in the US for, let's see how long, a bit longer, 302 milliseconds. But once you do it again, it caches and go to 0.016 seconds for you to access it. And with that, I'm going to go back to Dave.
Thank you, Gabby. Yeah, so that was just a quick tour of the storage products with a nice demo there that shows that when you use Google Cloud Storage, you don't just get access to storing the data in our data centers in the cloud, but you get access to our global network to bring that data to you or to your users wherever they may reside around the world, which is just an incredibly powerful way to store and manage content with us. So with that, let me pass over to my colleague, Tobias, who will talk us through the very interesting databases part of the talk.
Thank you, Dave. Hello, everyone. Yes, my name is Tobias Ternstrom, and I lead product management for databases in Google Cloud. I'm very happy to be here, extra happy because Dave let me come on stage since Dave works on storage and everything above storage is UI. So anything you use a database for, it's just UI. Relational databases are slightly more complex UI, but still UI. So let's take just a quick look at kind of how we think about our database portfolio. And there are three main things that we want to accomplish for you. So one is, as you would expect, there are a bunch of databases that are used widely today, and we want to make sure that we provide these databases as managed services in Google Cloud. The second one is there are some problems that are tricky when it comes to databases. Again, Dave doesn't think they're tricky, but at least I think they're somewhat tricky. So we want to make sure that we solve these problems for you. Like one good example is with Cloud Bigtable, Firestore, or Spanner providing truly scalable services with different trade-offs depending on what you're trying to achieve. And then the other thing that we think is also very important is to provide an integrated experience. So the more databases and storage options that you have, the more you have to do, like what Dave mentioned earlier, ETL, like extraction, transformation, and load, or gluing these services together. This we want to minimize over time. So make sure that these services actually talk to each other in a reasonable way. And there are tons of storage options and database options. And generally, when working with databases and storage, it's super important to spend some time looking at what is really your use case and what's really valuable to you. One of the things that I can just mention that at least I find is helpful is to think about the value of your data. And so you can think of data as a spectrum from super high value to lower value. And you might think, so like, what does value mean for data? Like, all data is valuable. It tends to be related to actionability. So the more actionable your data is, the more valuable it is. And it also tends to be that value is not that I'm not okay to lose less valuable data. But less valuable data, I might be okay with, for example, less ability to query over or slightly longer latencies and things like this. Like a good example would be an order. Like you want to track an order or a customer. That's a very good example of super high value data because it's super actionable. Like an order comes in, okay, we need to ship something, we need to send an invoice and so on and so forth. Whereas maybe collecting IoT information from some devices, some of that data might be actionable, but a lot of the data that you collect may not be actionable yet. You want to keep it around because maybe in the future, as you do analysis of this data or machine learning and so on and so forth, it becomes valuable, and then you want to kind of increase it up the value chain. So that's something to kind of keep in mind. But overall, when building applications, it's super important to be super pragmatic and look at what's really your kind of requirements. So in terms of our database products, we have Cloud SQL. Cloud SQL is fully managed databases. Today we offer MySQL and PostgreSQL. We might soon offer something else that I can't talk about. And this, I should be very clear. So MySQL and PostgreSQL and managed database services are super strategic to Google Cloud because we know lots of you use it. And it's super important to you. So we have to make sure that we have a great experience for these managed services. And you use these for lots of things. And there are lots of examples where something like MySQL or PostgreSQL is, for example, a much better solution than something like Cloud Spanner from us as well. So there are trade-offs between all of our products. Another product that we offer is Cloud Memorystore. This is fully managed Redis. And this is obviously if you have caching type solutions. And again, it takes away the mundane tasks of managing, patching, installing, and keeping track of the data. So I would like to invite Gabby back on stage to give us a demo of using Cloud SQL for PostgreSQL.
When you go to the SQL tab on the Google Cloud Console, you're going to have the option to create an instance or migrate your data. For now, I'm going to create a Postgres, and we just released yesterday Postgres 11. And I'll be creating an instance here with Postgres 11 for us. So PG11, I'm going to create a secure password. And when you deploy, you can select your zone. But one of the things that I find it most amazing about the Cloud SQL is the ability of choosing which size of machine that you want, up to 64 cores, and if you get it to 64 cores, up to 416 gigabytes. That will influence the number of connections that you have on your database. So I'm going to create a bit smaller one. We recommend using SSD, and one feature that we have that I didn't see elsewhere yet, it's the auto increase. And when you change disks, okay, you can start with 10 gigabytes, but you know you're going to store about 50 or 100. So if you put it already 100, you increase a bit your IOPS to query all those other 10 or 50 gigabytes that are still there. So it's not just about how much you're storing, but also how fast you're going to query that and how fast you're going to have the response over the data on the disk. Once you do that, you just hit create, and it's going to be created there. And while this is created, I'm going to show you an application for you. So let me see here. This is a Python application. It's really small, using Flask. And I'm going to be showing to you it running first on a local machine as a dev environment with Postgres. I'm going to set up. So Python. I think this is the right IP address. Oops. I'm sorry about this. Okay, it's not working, but that was supposed to be that tabs versus spaces one.
Did you break the internet, Gabriela?
I think I did, Tobias. I think I break the internet. But that's my local environment. Let's try to make it work on Cloud SQL. So with Cloud SQL, we have a thing called Cloud SQL Proxy that allows you to connect from anywhere without having to worry about whitelisting IP addresses and that kind of security concerns. So with Cloud SQL Proxy, I'm going to stop my database here. Because once you do that, it's going to be a transparent connection. Your machine is going to think that's connecting to localhost, but actually it's connected to the Cloud SQL instance. So right now, my proxy is ready for new connections. And I'm going to start the application again. Let me start in here. Let me get the IP address. Maybe I was on the wrong one. Let me see. It is working. So if you want to access, this is a simple application, tabs versus spaces, and it's running on Cloud SQL right now. And if you saw, I didn't have to change anything on the connection string right now, because it still is on localhost, as we can see here, and it's connected to Cloud SQL over the cloud, just using the Cloud SQL proxy. If you need to change permissions or anything else, you just use the IAM tool to change the permissions if who can or cannot connect to your database. And with that, I want to go back to Tobias.
Thank you, Gabby. Yeah, if you use Cloud SQL, the Cloud SQL proxy is super practical to make it super easy to switch between your local dev environment, which lots of people use on their laptop, into Cloud SQL. OK, so let's take a look at some of our other database products. Cloud Spanner, as Dave mentioned, is our scalable relational database. So it's a scale-out database, meaning that you can run it on one or many nodes. And it also separates compute from storage and allows you to scale these completely independently. So for example, if you have a Spanner database set up, and again, it's relational, so regular kind of tables, rows, columns, things like this, and you need more compute power, you can tell the system, OK, I'm going to go from 1 node to 100 nodes. We scale you up. It's completely online. You're now running on 100 nodes, and you have obviously a lot higher throughput with 100 nodes. Your data doesn't need to move around because the 100 nodes are, again, separate from your storage. And you can run through the spike, and as soon as you don't need the CPU anymore, you can scale down to whatever number of nodes that you need in order to run your workload. Now, this obviously comes at a cost, right? In terms of, not in terms of price, but in terms of performance. So generally, a scale-out database doesn't give you as low latency as something like a PostgreSQL instance, for example, that is completely local to your machine, or where data is closer to the compute, if you will. So this is one of these examples where you have to think about what is super important to you. And it also depends. So Cloud Spanner gives you a couple of interesting features. One of them is that you can scale the data either within a region or across the world. And when you choose to scale data with Cloud Spanner, all of the data is always consistent. Meaning when you read the data, you know that whatever you read is the absolute last committed, up-to-date data that we have. You can also do some things in order, and as you can expect, if I use something like Cloud Spanner on a global instance, there is some penalty in terms of latency, since we have to make sure that it's consistent across the world. So instead of talking, low kind of single to double millisecond latency, you may be talking something like 100 milliseconds. It depends on the use case and so on. But it's very, very useful. Because it turns out consistency is one of these tricky things that tends to create bugs in applications. So whenever you go down an eventual consistency path, your app better be smart enough to be able to handle that sometimes the data that you see isn't necessarily the latest up-to-date data. Right? And again, comes at a cost, and you have to look at what is more important to me, maybe lower latency, higher throughput, or consistency. The other thing, obviously, is that Cloud Spanner is relational. So if your data, per definition, doesn't fit the relational model, it's probably not the right pick for you. But it enables you to run a database from a couple of gigabytes in size up to literally petabytes in size, and from hundreds of queries per second up to millions of queries per second. And again, with dynamic scaling, so you pay only exactly for what you need in terms of compute. Now, contrast that with Cloud Bigtable. So Cloud Bigtable is our NoSQL key value / wide column store. And Cloud Bigtable is instead focused on high throughput, low latency. And we currently have in beta global Cloud Bigtable, meaning that you can have replication between Cloud Bigtable instances across the world. And this is a big difference between these two products. So if I go and write a bunch of data into Cloud Bigtable, it's consistent in the cluster, as we call it, that I write to, so whatever zone that cluster is in. But if I write to a cluster in North America and then I at the same time go and read from a cluster in Asia, I'm not going to see exactly the same data, right? There is some latency in terms of the replication in between, whereas with something like Spanner, I would see exactly the same data. And again, this is a trade-off. It's also a trade-off in terms of high availability. So Cloud Spanner offers 5 nines availability, but it is dependent on that the Google network is connected. Right? So all of the information flows for Cloud Bigtable and Cloud Spanner and the next product I'm going to show, Cloud Firestore, on Google's backbone. But let's say someone cuts a cable, for example, the Google cable between, or all of the cables, if you will, between, let's say, North America and Europe. In this case, Cloud Spanner has one of the regions, which is the writable region, which manages and owns the writes. Okay? Even if when you read, everything is consistent all over the world, right? So your app per se is always seeing a consistent view of the data, but there is one region that owns the writes. So in this case, if this happened, Cloud Spanner wouldn't allow you to read or write from the non-primary region, right? Because of the fact that then it could be inconsistent. Whereas Cloud Bigtable, which is eventually consistent, would allow you to write, and at some point, someone connects the cable again, or whatever happened, then you can continue, then things synchronize, you'll have merge conflicts, things like this, potentially depending on the app, right? But everything continues to move. And these are fundamental decisions that you have to make. And it's also important to note that even within one application, you may want to make different trade-offs. Right? You may want to use something like Cloud Bigtable for some parts of the application and something like Cloud Spanner for other parts of the application. Like Dave mentioned, for example, metadata in cloud storage is stored in Spanner to make sure that it's fully consistent. And then we offer Cloud Firestore. So again, Cloud Firestore is our NoSQL document store. And Firestore is optimized also for a completely consistent view of the data. So it's a document store that's completely consistent. You can run it multi-regional, i.e. across multiple regions or within a single region. Within a single region, we offer a 4-9 SLA. Multi-region, same as Spanner, we offer a 5-9 SLA. The difference here is, again, it's a document store. So if you fundamentally are building an app and a document store is like the right model for you, and Cloud Firestore is a good choice. The other thing that's interesting with Firestore is that it's completely serverless. So Cloud Bigtable and Cloud Spanner both offer you completely elastic scaling up and down, but you still have to tell the system, hey, give me more nodes or give me more CPU, or I don't want the CPU anymore, please take them back. Whereas Firestore scales completely independently. You don't have to tell the system what you need. It scales with your workload. It scales with your workload. BigQuery, again, is our data warehouse. BigQuery is similar to Firestore in the sense that it's also a serverless model, meaning that you don't have to provision compute. You use the data, you pay for storage, and you pay for consumed CPU, if you will, or consumed resources. And BigQuery also offers you this kind of infinite scale where you can scale to more or less any data size. And depending on your use case, this may very well be the right product for you. So the more of analytical use case you have, the more you're interested in using BigQuery. And again, it's very common to see that you're using all of these database products together. You're using maybe Cloud SQL for MySQL for something, Spanner for something, Bigtable for something, and BigQuery for analytics. So with that, I'd like to invite Alok and Kodim up to stage to give us a demo of Spanner and their company Stream. So Stream is strategic partner of ours that do basically replication and migration of data into Google Cloud. Thank you.
Thank you. Thank you, Tobias. It's actually Tobias, so I just correct that. So today I'm going to show a demonstration of, now that you have these wonderful endpoints on the Google Cloud, how do you actually use them? How do you actually move your data into them? And I'm going to talk about, in this demo, how we move real-time data from your applications, from an on-premise Oracle database into Cloud Spanner. So before I get into the demo, just a little bit about Stream. Stream is a next-generation platform that helps in 3 solution categories. Those are cloud adoption, hybrid cloud data integration, and in-memory stream processing. Today, I'm going to be focusing on the cloud adoption, specifically how do we move data into Spanner. So with that, we're going to jump into the demo. OK. So what you see on the screen is the landing page, and I'm going to keep this going pretty fast. We're going to step into the apps part of the demo. That's where the data pipelines are defined that help you move the data from on-premise to Spanner in this case. What you are seeing there are 2 pipelines. One of them is meant to do an initial load or an instantiation of your existing data onto Cloud Spanner tables. And the other one, while you're instantiating it, is also meant to catch it up. So while you're actually moving the data, you might have very large tables, for example, or massive amounts of volumes. So how do you actually go ahead and not lose any data? And all of the consistency things that we heard about from Tobias earlier, it's important that while you're moving the data, you also don't have disruption to your applications and to your business. So let's step into the pipeline here. So this is a very simple pipeline. It actually has a simple flow. You have at the top a data source, which is, in this case, Oracle. It's running on-premise. So we connect into this Oracle database. It has a line items table. We're going to show you a movement of about 100,000 records. And also, there's an orders table where we're going to show you the delta processing. The way this application is constructed is by using these components on the left side of the UI in the Flow Designer. And so you drag and drop one of these things, and you push them into the pipeline, and that's how you actually construct your data flow. And once we actually go, we can also step into the Spanner target definition. And this is your service account and the connectivity and the config for your Spanner Cloud Spanner system. We're going to next deploy this application or the pipeline. And once we deploy it, this is where you can sort of see that I can actually run this within the Stream platform. This can be run either on-premise or on the Google Cloud. We want to probably show Corinne that there's nothing available yet in the tables on the Spanner side. So let's go ahead and execute a query against a line item table. And in this case, you're seeing that there are 0 records there. And you can take my word that there's 100,000 records on the Oracle side. In the interest of time, we'll assume that. And let's go ahead and run the application. And as soon as we run the application, you can see that in the preview, in the lower part of your screen, you can actually see the records running live. This is while we're uploading the data and applying them into the Spanner, into Cloud Spanner. You can see that we have completed 100,000 records, and it was pretty fast. This morning, I'd done 1 million records, so I was holding my breath there. But that was pretty fast as well. So now you can see that the data part is completed. I mentioned to you that there's a second phase here. That's the change data capture phase. So this is while you're actually executing this query. Of course, this query is consistent as of a specific snapshot at Oracle. There's also DML activity against your application. So how do we actually take this data? This is the second pipeline now. So we can step into pipeline number 2. Corinne's already deployed it. And in this case, we use a special reader, and that actually operates against the redo logs of the Oracle database and actually monitors that, so it doesn't actually have any impact on the production system per se. Impact as in, like, it's at least not doing any query impact there. We grab the data from the redo logs, and then we are going to reapply that as DML, as inserts, updates, and so forth on the Cloud Spanner system. So let's go ahead and run this application. We are going to generate some DML using a data generator. There we go. OK. And let's go ahead and run the generator. And you'll see that there's a number of inserts, updates, and deletes against the orders table. And now let's switch over to the Cloud Spanner system and query the orders table here. As you can see, there's data in the orders table. This was also something that was just propagated. So this is sort of like the two-phased, very fast demo of how you get data from your on-prem databases into Cloud Spanner. And of course, this can work against other databases that we support as well. And this is available in the Google Cloud. So with that, I'm going to hand the control back to Tobias.
Awesome.
Thank you.
Thank you, Alok. Thank you, Gordon. Cool. It's good to know that we can get data into the database as well. In conclusion, Dave gave us a history of databases, or both storage and UI. And hopefully you got a sense of that we have a lot of different both storage and database products in Google Cloud, and that they very much target different use cases. So again, depending on what your primary use case is, you should evaluate and find the right tool for the job. And also, as Dave mentioned, for like 30 years or so, there was basically one tool. It was the relational database. I always say that's the hammer of database management. And you can use hammers for most everything, right? But like if you're going to cut down a tree, it's going to be tricky with the hammer, and you should probably evaluate using a saw or something like this. Screwdrivers, very bad for cutting down trees. Also, always spend the time to kind of evaluate the solution and see what actually works best for you and your specific use case. And this is generally what takes quite some time, especially to figure out what is most critical to you. Like generally, the hardest question to answer is what is more critical: availability, for example, or consistency. So these are things you have to look at, and also it's important to look at what do I need today, and what am I going to need over time, and how easy is it to transition between different databases and storage options. And that's, again, one thing that we think is super important for us to provide you is a seamless experience to actually move between and use these products together. Because we know it's like things change, businesses change, applications change, priorities change, and what is the right product for the job today may not be the right product for you tomorrow. So with that, thank you very much for coming, and we'll stick around here and answer any questions you may have.